Application of Bernoulli's law. Bernoulli's law is simply the energy at point 2 is same as energy at point 1. It is the law of energy conservation, so it's not really nothing new. However, in the fluid context, we're going to use the shower head example. Say, for example, the water is coming in the house. These pipes are typically about 3/4 inch diameter, and then that goes to a shower head, for example, like this, with some holes in it, small hole. So say this is my point 1 and this is my point 2 at the shower hole, the head of the shower. So the total energy I have at point 1 in terms of, it can be in a fluid system, is the pressure, static pressure energy, which is P1 by gamma, plus the velocity energy, V squared by 2z, plus the elevation energy G. That will be the same for point 2, P2 by gamma plus V2 by 2z plus G2. So first, to solve Bernoulli's equation, we have to calculate the velocity. Assume that we have a flow rate of 10 gallon per minute in the system. So from that continuity equation, which is Q is equal to area times velocity, so we can find out the velocity is equal to Q by A. So flow rate is 10 gallon per minute. Then let's convert that gallon to inches. One gallon is 231 inch cube, and then 1 minute is 60 seconds. Also, we have to divide this by the area. So the area right here is pi by 4 d squared at point 1. So we can say simply, I calculated that. So the area at point 1, pi by 4 d squared, 0.75 inch square. I found that 0.4418 inches square. So I'm going to use that here. 1 by 0.4418 inches square. So I found the velocity at point 1. I calculated that to be 7.26 foot per second. Now this will come in inch per second, then you convert that to foot per second by 12 inches 1 foot. So this is the velocity at point 1. Now we have to calculate the velocity at point 2. So the area 2, I found total 50 holes, for example, in this shower head, and then the diameter of the hole, say for example 0.3 inch each of them. So the total area of would be pi by 4 d squared, 0.03, not 3, 0.03 inches squared times 50. So I found the total area for that is 0.0353 inches square, the shower head area. Now apply the same principle. I can do the V2 is Q by area 2, and then I calculated that 90.78 foot per second. So in the Bernoulli's equation now, I'm going to put that. Also, let's say at point 1, the pressure is given at 60 psi. So in the Bernoulli's equation, I'm going to write P1 by gamma minus P2 by gamma is equal to V2 squared by 2z minus V1 squared by 2z. I just rearrange this, taking this V1 in this side, and assume G1 and G2 are same, at the same level of elevation, or ignore the very tiny amount of elevation difference. So here V2 square is 90.78 by 2z is 32.2 foot per second square. This is in foot per second whole square, minus V1 I found 7.26 foot per second whole square. So this difference, the P1 by gamma minus P2 by gamma, I found that 127.14 foot of liquid, in this case water. Now we can write P1. So you can take this piece right here. P1 minus P2 is equal to, you can write 127.14 times the gamma, which is 62.4 pound per feet cube, water gamma. This is in feet. So P1 minus P2, I have found that 55.09 psi. Now this will come in pound per feet square. You convert that by using 1 feet is 12 inch. So that's how you get the psi right here. And then if P1 is 60, then psi, then P2 would be about 5 psi available right before the 5 psi available right before the shower head, a small tiny hole. Now remember, as soon as the water gets out of the atmosphere, it becomes, there is no pressure there, so then it's become atmospheric pressure. This 5 psi is just before when it leaves the shower head.